Who has?
It was 1, 3, 5, and 7.
Okay. You guys have already done these, supposedly.
Exactly. So I don't know why he's asking me to do them.
No. Okay, everybody look up here now, except people who are trying to clean coffee off of themselves or whatever. So number 5, 2 carts are rolling towards each other. One has a mass of 0.2 kilograms. It's going this way. And it has a speed of 4.5 meters per second. And then the second one is going the other way. How do we know it's going the other way? Because it says they're going towards each other. So it doesn't matter which way you draw this, but they need to be going towards each other. This one has a mass of 0.6 and a speed of 2 meters per second. And you can imagine they have little links on the front. So for part A, they're going to link together when they collide. For part B, they're going to bounce apart. If they link together, that's an inelastic collision. If they bounce apart, that's an elastic collision. So for part A, I guess I'm not going to go through the whole calculation, but you can think of, if you think of this in a top view, you have this one going 4.5 meters per second that way. The other one going 2 meters per second this way. We'll use a coordinate system with the x-axis in line with the direction they're moving. And so conservation of linear momentum says, this is the inelastic case for part A. 0.2 times 4.50, because that 4.5 velocity is in the positive x direction, plus 0.6 times its velocity vector. This one's moving in the negative x direction. And then those are equal to the sum of the masses. And you can solve for both of these components. That's the combined velocity after. And you'll get that Vy is equal to 0 since everything's happening in a line, and you can solve for Vx. Okay, let's go to part B. This is the elastic one. So we're just going to use the x component of conservation of linear momentum, and then we'll use the requirement the kinetic energy, total kinetic energy, is equal at both instants. So we have 0.2 times, so like equation 1 here, 0.2 times 4.5 plus 0.6 times negative 2 is equal to 0.2 V1 plus 0.6 V2. That's one equation for two unknowns. And then we'll use 1/2 times the mass of the first one times the velocity speed squared plus 1/2 times the mass of the second one times its speed squared is equal to 1/2 times 0.2 times V1 squared plus 1/2 times 0.6 times V2 squared. Now you have two equations for two unknowns and you can solve it. What? Yes. So let's think about what's going to happen here. So without doing the calculations, in the inelastic case, which direction are these, is the combined mass going to be moving after the collision? And how would you figure that out? Yeah, you can just look at the two. Well, here, let's take a minute and just think through this, okay? So question 1, in the inelastic case, which direction will the carts be moving after the collision? Then the second question is, in the elastic case, which direction will each cart be moving? And what can you say about the speeds in the two cases compared to each other? Okay, so gather into little groups and just talk about this and come up with some answers, and then we'll think through it, okay? So for the inelastic case, which direction will the carts be moving, and how do you know? Okay, they'll be moving in the negative direction, and how do you know that that's true? Yeah. Yep.
Like 0.9 and 1.2.
Yeah, so exactly. So you have a positive momentum. You know, you're the one who asked for me to do these questions, and you've been talking to them about other stuff the whole time I've been trying to explain this stuff. Okay, so this is a positive momentum. That's in the positive x direction. That's a negative momentum. So which one of those two is bigger? This one is negative 1.2. This one is 0.9. And so the total momentum is in the negative x direction. And so that means that the velocities have to be in the negative x direction afterwards. Okay, in the elastic case, what directions are these two going to be moving? Now they have independent directions. Well, one of them is going to still be moving in the same direction. So let's think about this. If they had the same mass and the same velocity, okay, so if they had equal and opposite momentums, then they would hit and they would both go in the opposite direction.
Would they both just, even if it was elastic, if they both had identical everything, would they just stop? Oh no, because we're assuming.
No, because that's what they would do if it was inelastic. But if it's elastic, they have to keep the same, so they have to bounce, you know. And so if they come in with the same mass and the same speeds, they bounce away with the same speeds, just opposite directions. So use that as sort of like your starting point, you know, like your. So what would happen here? Well, this one has more momentum, right? So when they bounce, this one is going to, well, I guess you don't know, you don't exactly know the direction here, but you know that this one isn't going to be, it's going to be less than a speed of 2 meters per second. It could still go this way, or it could trickle this way a little bit, you know, but you know that it's going to bounce back. If it bounces back, the speed is going to be less than 2. And this one is going to bounce back faster than it came in, because it's going to get some of the momentum going that way. Okay, so we know that this one. Well, so in the inelastic case, they're both going to move in the negative direction, right? In the elastic case, this one's going to be moving in the negative direction. So in which of those two cases is this one going to be moving faster? In both cases, it's going to be going this way. In which case is it going to be going faster? In the elastic collision, it's going to be going faster that way. So, like, if your goal is just to get this thing going as fast after the collision as possible, you want that to be an elastic collision. Number 7, did you ask about? Yeah. Okay, so 2 carts roll towards each other. Okay, so this one, it's inelastic. The first one it says they're rolling towards each other. It doesn't matter which way they're going, just that they're opposite directions. This one has a mass m and a speed 2v. And the second has a mass of 1.5 m and a speed of v. And it's inelastic. So if you think of a top view, it looks like this. There's m, there's 1.5 m. Here's 2v, here's v. Conservation of linear momentum, inelastic. says m times 2v plus 1.5 m times negative v is equal to, add up those two masses and you get, no, 2.5. 2.5 m times v final. So 2 mv minus 1.5 mv is equal to 2.5 mvf. And we're trying to find vf in terms of v. So the m's cancel out, and you get 0.5 v is equal to 2.5 vf. So vf is equal to 0.2 v. Any questions about that? Okay. All right, so who remembers what we were talking about last time?
Mass moment.
Yeah, okay, so
Moments.
yes, a lot of stuff with the word moment in it. So we're going back to rigid body kinetics. Remember that movie with Michael J. Fox? And rigid body kinetics, the main equation of motion is this rotational version of Newton's second law, I'm going to call it. That's not, no one else calls it that, but that's what I'm going to call it. I've never heard a name for it.
So it's just like.
People don't call it that, but I understand what you're saying. That's it. You do derive it from Newton's second law, but right. So, and this equation says that if you take all the moments about this point A, that's equal to the mass moment of inertia about A times the angular acceleration. And there are two restrictions on what this point A is. First, it can be a fixed point, like a hinge connected to the ground. It has to be fixed in your coordinate system. Or it can be, if there's, because a lot of objects don't have a point that's fixed in the coordinate system. It has to otherwise be the center of mass of the body. We're not going to do problems like this one. For us, this is going to be the story. But when you're doing rigid body kinetics for things that are like there's no part on the body that's fixed in your coordinate system, like a muffin you throw or something.
I do that quite a lot.
Let's see. I don't believe you. Then you have to use the center of mass of the muffin, or it can be other things besides muffins. The center of mass. Don't write this down. The center of mass. You can do it that way if it has lines of symmetry. Yes, that's exactly right. And everything we're doing has symmetry, And so we can do it that way. But a thing like a muffin, well, I guess it has one plane. It has planes of symmetry because we're talking about 3D. But those planes all intersect in a line down its center, you know? So how do you find the center of mass of something that doesn't, that all its symmetry lines or planes of symmetry don't intersect at a point? No, you go like this. You do the following thing. Yeah, x, y, z, so the coordinates of the center of mass are equal to 1 over the total mass times the integral of x, y, z, dm.
Wait, is that the same M that's on the outside, or are those two different M's?
That's on the outside.
Of the integral?
Yeah, well, the big M is the total mass of the whole thing, and dm is the little pieces you've broken it up into. Those are positions that's a position in the coordinate system. So wherever your origin is, those are the coordinates.
Are those lines in
No, those are lines. That's a symbol for the centroid, actually, rather than not the center of mass. Usually those are the same thing. So that's how you do it. So aren't you glad we're not going to do any calculations involving muffins? And actually, in practice, like when you're in an engineering class where you have to use centroids, mainly, you know, the way that we did, I gave you that ugly integral formula for the mass moment of inertia. But then we just used it, or we didn't do it. Somebody else just used that integral definition to come up with formulas depending on the length and the mass. And those are easy to use. And it's the same with center of mass. Although I've never seen one for a muffin, but I've seen them for many shapes. And you just use these formulas. So.
The muffin would be hard to like
Yeah, you'd need a function defining the. You do it as a surface of revolution or a volume of revolution. Yeah, that's true. You'd have to break it into two different functions. What? Oh yeah, like not homogeneous all the way through. Yeah. Oh yeah. Right.
Anyway, we're not doing muffin.
The average muffin, I think, is perfect on the top because all the bumps on the different muffins average out in the. Okay. So we talked about mass moment of inertia. Yep. That was for the mass moment of inertia. That means you're integrating over the whole mass. Your integral, so the bounds of integration are the whole mass. You know how when you do a definite integral, you do it like say from the interval from -2 to 4, and you have a -2 on the bottom and a 4 on the top. Okay, then you're doing this integral, and the bounds of the integration are this interval on the number line from -2 to 4. Okay, this is a three-dimensional thing, but the boundaries of your integration are this entire mass. Okay, I don't think it makes sense with anything that you do in Calc 2, but it's stuff that you'll do in Calc 3. Okay, but I think I did an example, right, where I did turn it into just a regular integral. Didn't I do an example? It was a little confusing. I calculated the center of mass for a circle, I think. for like a disk. Yeah. Yeah, we did it, but don't waste too much time thinking about it. So we needed to define two things before we could use this equation. We already knew the angular acceleration. We know what that means. We needed to define the moment and the moment of inertia. So the mass, moment of inertia, and we talked about that. Done. And then we need the moment of a force. Oh, this also should be about a point. The moment of a force about a point. And that's the one that we're on. Okay. So we started out with the cross product. So to define the moment, we needed the cross product. And so you can think of it this way. If, let's say, let u equal ux, uy, uz, and let the vector v be vx, vy, vz. Use different component names before, but then there's two definitions of the cross product. The first one is the component one, and if you have the components of these vectors, you can get the components of the result. So u cross v time, it's a x, yeah, time symbol. It's a cross instead of a dot, yeah. Right. That's true. I never even really thought about that before. Those are both ways of writing times, but yes. Yeah, you do the dot product and right. Yep. Okay, so the x component, you cancel out the top row, or cover the top row and then go diagonally this way minus diagonally this way. So ux, no, I didn't cancel the top row. uy times vz minus uz times vy. Then for the y component, we're going to take the negative of this, but we're going to do the same thing. So cross out the y components, and you get ux times vz minus uz times vx. And then the z component, cancel, cross out the bottom row, and you have the quantity ux times vy minus uy times vx. Okay, so that's sort of a messy thing, and it's sort of surprising that it comes out to be exactly equal to this second definition, but it does. So the second definition is In 2D, I think usually it's going to be easier, although both are useful at different times. But you can also think of it as the magnitude of u times the magnitude of v times the sine of the angle between them. And then the direction, that's the magnitude of the vector. So we need a direction, and the direction is according to the right-hand rule. Okay? If you're in 2D, when we're talking about moments, there'll be an easier way than thinking about the right-hand rule. And so when we apply this to moments, I'll tell you what that is. One thing that's going to be useful with this cross product is, in some important cases, the magnitude of the cross product is just equal to the product of the magnitudes. What's that case? When is the cross product of u and v just equal to magnitude of u times magnitude of v? Exactly, if they're perpendicular. Yep. So if u and v are parallel, the cross product is 0. And if u and v are perpendicular, the cross product is just, you multiply the two magnitudes together. It still works, but it's harder to calculate that angle between them. You know what I mean? Because it can be at a funky angle. But yeah, any two vectors, I mean, there's some plane. So any choice you make of two vectors, there's some plane that has both of them in it. And then in that plane, you can find that angle. But doing it mathematically is really a pain. In 3D, you pretty much always just want to use that first definition. Okay.
I know it's from a hand a couple times.
Yeah.
The right-hand rule is just saying that, like, the direction is going to be opposite to the other direction.
So the right-hand rule always is a relationship between a rotation and a vector that's perpendicular to the plane of that rotation. Okay. So the rotation is represented by your fingers always. Yep. And your thumb represents the vector that's perpendicular to the plane of rotation.
So it's always going to be, the direction is always going to be perpendicular to the plane of rotation.
Yes.
I can figure out the plane of rotation.
Well, in our case, it's easy because we're doing everything in 2D. So the plane of rotation is the XY plane. And that means, so what axis is perpendicular to the XY plane? Z. So that means that our cross products are always going to be in the Z direction. The right-hand rule. Because if you're, so if you have the XY plane, and you're about to see something shocking. So with angular velocity and angular acceleration, what's positive and what's negative? It's the opposite. Yeah. Right. Positive is counterclockwise, negative is clockwise. Okay. So now, think about a rotation that's counterclockwise. Yeah, well, that's the, so your fingers represent that rotation. Which way is your thumb pointing? Yep, and is that positive or negative Z? Positive Z. So that's So the right-hand rule is the reason that counterclockwise is positive and clockwise is negative. Okay. But in 2D, you can just think of it as clockwise and counterclockwise. In 3D, you can't, so you need a more general thing, and that's the right-hand rule. And notice that in 2D, so in 2D, clockwise and counterclockwise are defined. That's fine, you know, everything works out. But if you can move in 3D, you realize that nothing, clockwise and counterclockwise don't mean anything. Because if I draw a counterclockwise rotation on this tabletop, if someone can sit under the table and watch my hand, they see a clockwise rotation. Okay, so that's why the right-hand rule really underlies all that. Okay. Yes, I agree. Now we're going to apply this to the moment. Of a force about a point. Okay, so let's say that the body that we're dealing with is this thing. Okay, you say, okay, so why did I draw that shape like that? Why did I draw it like a blob? I'm just trying to make it clear that the shape doesn't have, the body itself doesn't have anything to do with this definition. Okay, it can be anything. It can be a circle. Yeah, I thought it looked sort of like a buffalo going down a hill. No, an American bison. Yeah, not a buffalo. Okay, so let's say that we have, so here's our point A, okay? That's the point that we're calculating the moment about. That would be, so in order to use this rotational version of Newton's second law, what are the candidates for this point A? What physical things? Center mass, or for us, it's a fixed point like a hinge. And let's say that there's a force applied over here, this point P. Okay, so the force, let's say it's like this. Okay, so that's the force F. And we're going to define a row vector that goes from A to P. And you have to remember this or you'll get your answers wrong. So this is the row vector. So let the row vector go from the about point A to the point where the force is applied. Then the moment about A, no, it doesn't have to be. Then the moment about A is equal to that row vector crossed with the force. And really this is a vector, this moment, although to us it's really going to only have one non-zero component. That's right. But the idea is, so imagine that point A is a hinge, okay, that it's free to rotate around that point A. If you apply a force at a distance like this, it's gonna try to make this body rotate around that hinge. That's what a moment is measuring, the tendency to rotate something. Yes?
You said the tendency to rotate.
Yeah. I mean, there could be friction, but we deal with that separately, you know.
Yeah, but
It's an angular acceleration because it goes with this equation. So the body has a certain, it's either easy or hard to rotate based on how big that moment of inertia is. That's the figure skating thing, you know. And depending on how hard it is to get that body rotating, the moment determines how much angular acceleration you get. Right.
and how do we compute the inertia?
I gave you 3 formulas last time. Yeah. So I gave you one for a slender rod, one for a rectangle, and one for a circle. Nope. Yes. Oh yeah, for sure. We'll do examples. In 2D, if you go through the math, like the component definition of the cross product, you see that in 2D, the result has no x or y component. Those are just equal to 0. And the z component is the x times y minus y times x. So it's only the z component that's non-zero. So a lot of times we'll do this as if it's just a scalar value, but really it's a z component. Yeah. Okay, so let's think about the physical meaning of this. Or the intuitive meaning. Say that you have a bolt that's stuck and you're trying to turn it with a wrench. What? Yes. What did I do? An octagon? Yeah. That's funny. I've drawn bolts like that a million times, but you're the first person. I don't know if they're hexagons. I'll have to check when I get it. Oh yeah, hex, because you use hex wrenches. Well, dang it. I have to contact all my old students. And yeah, they've been getting moments from this whole time. Not really.
Okay, I was like, wait.
It's all changes.
Okay, so if you want to turn this thing and it's stuck, okay, you're trying to loosen it. Righty, tighty, lefty, loosen. So you're trying to rotate it counterclockwise. There are 2 things that work together to determine how successful you are at turning this stuff. One is the force, because you know if this is stuck and you just barely push with your finger, it's not going to turn. You know, you might have to pull on it a little bit. And the other thing is how far away from the bolt you apply the force. Okay. So if you apply the force at the middle, you know, you apply a downward force like this, you have less of a chance of making it turn, even applying the same amount of force as if you come all the way out here and apply the force. That's why the wrenches that plumbers use are like this long. They're huge. It's so that they can apply the force a long way from there. And I do a lot of work on bicycles, and I have a big plumber's wrench like this, and you have to be careful. Like if something's stuck and you use this to get it unstuck, you have to be a little careful because sometimes you'll start to get it turning. You'll think the thing's coming loose, and it's actually just ripping the bolt in half. Because you get so much leverage when your hands are a foot or 2 feet from what you're trying to turn. Well, let's think about this in terms of the. Okay, so. Yeah, that's right. So that's F. This here is the point P. This is the point A. And this is the vector rho. So let's think about this definition, okay? Let's think about the moment about A is equal to the magnitude of rho times the magnitude of F times the sine of the angle between them. So what's that equal to in this case?
So
These two are exactly right. If you apply that force parallel, it's never going to do anything. Yeah, or push on it. It'll eventually rip the bolt off the wall, but it won't ever turn it.
Just slide off.
And so in this case, you get like if this length was 0.2 meters. Rho, well, not necessarily. I mean, that rho you just get from going from the about point to where the force is applied always. Oh, yeah, so you put those two tail to tail and then just measure the angle between, the shortest angle between them. So in this case, if you put those tail to tail, you have your rho vector like that. You have your force vector like that. And so this angle is 90 degrees. So 0.2 meters times, let's say, 100 newtons.
So keep that always in this case we're assuming that the final force
And now to think about the direction of rotation, because this is a vector. You need to give the direction. Yep. It's the vector from A to P. You can think of it as a position vector where you have your origin at the about point. Put your origin at the about point, and then it's the position where the force is applied. Yep.
But can we always do that? Can we use like the Pythagorean theorem to simplify our vectors to one number?
You can always simplify to one number and then just use the sine of the angle between them. Nope. Not in 2D. Okay, but we still need, so this is a vector. We still need the direction of the rotation. So how do we know whether this moment is clockwise or counterclockwise? Yeah, so the direction of the moment and the direction of the angular acceleration are always the same. So you can just think about, for that force, just think physically, would that force make this wrench rotate clockwise or counterclockwise around that hinge? In this case, it's counterclockwise, and so it's positive. And really, it's, notice, really in 2D, the moment is a vector with x and y components zero. But since there's only one non-zero value, a lot of times just we get sort of sloppier to save time or whatever. We write it as a number, like a moment is a number. But in 2D, what you'll often see and often do is treat the z component as a scalar, as a number. Okay, so let's take a break until 9. Come back at 9, and then we'll do a bunch of examples. Okay, so let's say we have a rectangle that's 3 meters long and 1 meter tall. And we have a force of, let's say 100 newtons. And let's say that the about point is here. What's the moment produced by that 100 Newton force? Okay, well, the row vector is like this. So we have two ways we could do this. We could calculate the components of the row vector and the force vector and do the component cross product. That's probably easier in this case. Or we could find the angle between those two and take the magnitudes and the... Okay, so in this case, probably the components. So let's do that. Okay, so the force vector, what's that in components? The force is negative 100, 0, and I'm just, at least for now, I'm going to write zeros for the z's. And then the row vector, what's the component? That's the one that's 1, 0. Does it matter whether we do row cross F or F cross row? Yes, order matters in this. So the moment vector is 3, 1, 0. It's row cross F. And notice that, so cross out the first row, and 1 times 0 minus 0 times 0, 0x. Cross out y, you get 0 again, and that's always going to happen in the xy plane. And so finally cross out z, you get 3 times 0 minus 1 times negative 100, so positive 100. And a lot of times, well, the units here are Newton meters. A lot of times people just write this as 100 Newton meters. The positive means that it's counterclockwise. So look at this problem. If there's a hinge at A, does it make sense to you that that 100 Newton force would make it rotate counterclockwise? Yeah. This was easier because it's sort of a pain to figure out that angle, but we could do it. So to use the fact that MA is equal to the magnitude of rho times the magnitude of F times the sine of the angle between them. What's the magnitude of rho? Yeah. So 3 squared plus 1 squared square root is root 10. And what's the magnitude of the force? Yes. And how do we figure out the angle between those two? That's true. Well, you know the tangent of this angle is inverse tangent of 1/3. So is that a thing, inverse tangent of 1/3? Yeah. Degrees? Okay, but then that's just the angle, that's just this angle. You want to put these tail to tail. So this is rho, this is F. What's this angle? 108.43 degrees. And so then the moment is root 10 times 100 times sine of 108.43. And what do you get for all that? Hopefully you're going to get 100. And then there's one more thing you have to do when you do it this way. You have to think about the direction because this doesn't give you the direction of the rotation. So would that force make it rotate clockwise or counterclockwise around a hinge at A? Counterclockwise, so it's positive. And that's a Z component, but a lot of times we'll just write it like that. Want to see something else? No, you're not ready. Okay, I'll tell you. So notice, in some cases, it makes the problem easier to move the force along its line of action.
Both, when plugging it into our calculator. All of us. That's what happens when you.
That doesn't make any sense.
No, it doesn't.
Square root of 10, oh, I guess is 3 something. Sine of 108 is close to 1. Okay, so I guess that angle. Oh, this is the wrong angle. This angle is. That just emphasizes how. So this is 18.43. So it's 180 minus 18.43. So what's that? 161.57. Try that one. Yeah. Are you all right? Okay, in some cases, it makes the problem easier to move the force along its line of action. So let me show you what that means. Yes. It doesn't always help, but a lot of times it helps to move the force along its line of action. So look at what we could have done in this problem. If we move the force along its line of action at this point over here, then the row vector and the force would be perpendicular to each other. And we would have just immediately been able to say 1 meter times 100 newtons is 100 without worrying about the angles or anything. And it actually, in this case, would have made it easier to calculate the length of the row vector too. Okay. So summary of moment calculations. Without changing the problem, you can move any force anywhere you want along its line of action. And then second, you have 2 ways you can calculate the moment. It's equal to 0, 0, rho x fy minus rho y fx. Or it's equal to the magnitude of the row vector. So the moment is equal to magnitude of the row vector times the magnitude of the force vector times the sine of the angle between them. Remember, they have to be tail to tail for this. and this comes from counterclockwise or clockwise. Okay, so here's an example. Let's do this one on the board. Okay, so let's say this is 0.1 meters. This is 0.5 meters. This is where it rotates around, that's the hinge. And let's say we have a force of 30 newtons there. And a force of 80 newtons there. And actually, what? The center, yeah. And let's put another one here of 50 newtons. Okay. Calculate the sum of all the moments produced by those forces on that body. I'm going to do this by moving the forces along their line of action, and in this case, it's going to make this a lot simpler. But for part of your assignment, I'm going to have you go through, move it along the line of action and do it. Do it with each of the two other methods without moving it along the line of action, and just convince make sure that you get the same things for all of them. Excuse me. Okay, so I'm going to do it like this. So here's the about point. I'm going to move the 30 Newton. So here's the line of action of the 30 Newton force, right? So I'm going to move it to right here. Here's the line of action for the 80. And so I'm going to move that to right here. And here's the line of action for the 50. And so I'm going to move that to right here. And now each one of these forces is perpendicular to its row vector. You see that? The row vectors now are this, this, and this. Okay? And to think about the directions, you just have to think about which direction the thing would rotate for each one of these forces. So the moment about A for the 30 is 30 times 0.25. And then would that 30 make it rotate clockwise or counterclockwise? Clockwise, so this is negative. So that's what, 7.5? And then the moment about A for the 50, the row vector is 0.25. The force is 50. Would that make it rotate clockwise or counterclockwise? Counter, so that's positive. And so this is 12.5. And then the moment about A for the 80, the row vector is 0.05. The force is 80. Would that make it rotate clockwise or counterclockwise? Clockwise, so that's negative. And so we get And so the total moment about A is negative 7.5 plus 12.5 minus 4. So that is 1 Newton meter.
Yeah, that's what we got.
Nice. Okay, any questions? All right, yeah, it'll just take practice to put the sort of different options you have together. Yep.